Thank you.
Our next speaker is Ray Goldstein, who needs no introduction. He's the local Schlumberger Professor in the Department of Applied Maths and Theoretical Physics in Cambridge. He's very well known for his work on pattern formation and also in recent years on biological physics. As many of you will also know, he has been a winner of the Ig Nobel Prize for Physics, whose purpose is, indeed, for this, some of the work he will talk about today, whose purpose is to reward science that first makes you laugh and then makes you think. And a lot of Ray's work is like that. So not a lot, enough to win you the prize. I wouldn't say that's the majority. But anyway, we're looking forward to your talk today. Thanks, Ray.
Thank you, Mike, very much. When Andre asked me if I would speak in today's session, I was slightly hesitant because I'm not really an artist, although many of the things that I work on are motivated by aesthetics. But then I realized it was actually on my birthday, and I thought, well, what better present than a whole day of toys and games? So there we go. Well, thank you. No. But the other thing to say is that although I'm not an artist, I grew up in a family of architects, actually. So my father was an architect, and both of my brothers are architects. My sister-in-law on one side is an architect, and my mother's an interior decorator. So you might ask, what happened? And the answer, as my father said, is that actually I just work on a smaller scale. So that's what I'm going to talk about today. And I thought I could summarize what I'm going to talk about this way. So first I'm going to talk about this, and then I'm going to talk about this, and then I'm going to talk about that. Because as I was thinking about what to lecture on today, I realized that there was a series of problems I had worked on over the years which all boiled down to trying to understand these very elementary shapes that we find in the world around us, and it turns out they're all kind of the same shape. They're just permutations of the fundamental physics. So the first part of what I'm going to tell you about is a problem that we worked on about 10 years ago that actually is about understanding the shapes of stalactites. So stalactites are those iconic structures that you have seen pictures of and perhaps have seen in real life that you find in limestone caves. They're long and pointy, they hang from the ceiling, stalagmites grow from the floor. And you can find in the pseudoscientific literature, historical documents dating back all the way to the elder Pliny in the 1st century describing these things. But it was actually only about 100 years ago that the basic chemistry became understood, and it's only about 10 years ago that some idea of where this basic shape comes from. It looks like a carrot, and we want to try to understand where that comes from. So I'll tell you in the first part of my talk a little story of how some basic ideas in fluid mechanics and chemistry boil down to the discovery of a Platonic shape, and I'll explain why I call it that, that seems to be what is found in nature. So this work was done when I was at my prior institution at the University of Arizona, and Arizona and the whole Southwest are full of beautiful limestone caves, and one of them is a kind of scientific resource as well as a tourist attraction. It's in Benson, Arizona. It's called Kartchner Caverns. And when you go in, this is what you see. So it's deep underground, and it's full of these absolutely amazing structures. These are stalactites that can be several meters long, but there are many, many other kinds of structures that you find in limestone caves. Another example are these things called soda straws, which are basically hollow tubes that hang from the ceiling, and when they get plugged up, they eventually become the inside of a stalactite as it grows. But there are also these fantastic structures called draperies. I don't have a theory for these yet, but maybe that's what I'll do next. So they really look like curtains hanging in your living room. They're large, this big, and they have this beautiful scalloped edge to them, and if you look at them from below, you'll see this wonderful meandering structure. And I don't know about you, but when I look at an object like this, I say there's got to be a law for this. There's got to be some mathematical explanation of why there's this regularity. What sets the wavelength? What sets the thickness? How does this come about? So that was the origin of our work on stalactites, and it was a random comment by an undergraduate in my lab at the University of Arizona that led us to make a connection between something else we were working on and soda straws, and that led eventually to what I'll describe now. So I want to do some just basic physics and mathematics to try to understand what matters for stalactites. So the basic process is this. Water from above the cave percolates through the soil, gets saturated in calcium carbonate actually. And when it emerges into the cave, it has too much carbon dioxide for its own good, and it outgasses it, just like the sparkling water I just opened over there. It outgasses the carbon dioxide just a little bit. That raises the pH of the water that's flowing down the surface that exists. That precipitates calcium carbonate on the surface, and it goes on. Now, stalactites and other structures grow very slowly, centuries on end. So for instance, the typical growth rate might be a centimeter a century. So you have this poor stalactite sitting there constantly with water flowing down it, and the question is what length scales and time scales matter. So the typical drip rate might be something like 40 cubic centimeters an hour. So drip, drip, drip. So in the century that it takes to elongate 1 centimeter, an entire swimming pool's worth of water has flowed over this poor stalactite. And if you do the math, you discover it had about 5.5 kilograms of calcium that could have deposited on the stalactite. But actually only about 200 grams did so. So this is just a slight depletion of the calcium in the water as it goes down. And the length of a stalactite could be a few meters maybe. Its radius is perhaps like this. The fluid flow I mentioned, but that water layer thickness is really small. It's 10 microns. It's 1/10 that of a human hair. And the fluid velocities are very small, millimeters a second. So this is a world of low Reynolds number, meaning it's dominated by viscosity. Now the time it takes for carbon dioxide to diffuse out of this thin layer of thickness H is something like 1/10 of a second, but the time it takes for a parcel of fluid to go down the entire length of the stalactite is about 1,000 seconds. And the time it takes to grow is something like 1,000,000 seconds, order 1. And so there's a huge separation of timescales, which makes the analysis much simpler. So basically, if you were to cut a cross-section of a stalactite, you'd see a little fluid flow in a thin layer here, thickness H, which would have 0 velocity at the calcium carbonate surface, and it would have 0 derivative at the air. And so it's just a function that's linear and quadratic. You can calculate from that the typical flow speed in here and the flux of fluid coming down. And when you put this all together, you can find that the layer thickness in units where you measure the flux of water in cubic centimeters an hour and the radius in centimeters is typically about 10 microns. So really small. And the fluid velocities are about millimeters a second and scale in a funny way with those fluxes. And depending upon the thickness of the fluid layer, you either have some inertia in the flow, or typically when the layer thickness is down around 10 or 20 microns, the Reynolds number is really small, so there's no inertia at all. Okay, so the chemistry of this is well known. There are a whole bunch of different chemical species involving dissolved carbon dioxide in the water. And you can write down all the chemical kinetic equations, and it's kind of boring. But there was a key piece of work that was done by Boomen and Drebrod some years ago, which showed that the slowest chemical reactions in the problem are those that produce the CO2 that then outgasses. And so you can write down these, by the law of mass action, you can write down these chemical kinetics, and we know the timescales of them. And so the problem for the applied mathematician is, I have a thin layer of fluid of thickness that I know, I have chemistry going on there, and there's some rate at which things precipitate on the surface. And how does that rate depend on things like the fluid layer thickness? And what you discover after you solve this problem, and I won't show you how, is that the flux of calcium carbonate onto the surface depends on the excess concentration of the calcium in solution compared to the saturating amount, obviously, some rate constant, but most importantly, the thickness of the fluid layer, as long as that layer is thin. So in fact, all I need to know is how thick is a fluid layer flowing down an object of cylindrical symmetry, and I can just immediately calculate the flux. Well, that's good because this layer is so thin that I can just basically do a local calculation as if this was just a plane at every point. And from that, I get the growth rate, the normal component of the velocity with which this surface moves is this function of position. It depends on the local radius, the local angle with respect to vertical to give me the gravitational force, and the characteristic length that's given by the parameters. So there we go. This is a law of motion. It's a geometric law of motion. It says if I know where I am and I know the slope, I know the rate at which I grow. And you can put in numbers, and it's typically about some fraction of a centimeter a year. It depends on the pH, and it changes sign, so you can have situations where it will erode and situations where it will grow. And the most important thing is that if you actually take a typical stalactite shape and look at how this depends on the angle, the tangent angle, you find there's a huge enhancement at the tip, because as the radius is getting smaller, there must be more fluid in that layer, because there's no evaporation that occurs in a limestone cave. I can assure you, in most of these caves, you go in there and it's like a sauna. So it's not as hot as a sauna, but it's as humid as a sauna. So we did some numerical studies of this model, and what we discovered was that if you start with some arbitrary initial little seed at the top, it grows as if it's just traveling and emerging from the ceiling. So that says that we don't have to solve this as a full, complex mathematical problem. We just have to look for a solution in which it's uniformly advancing, well, down. So you do the mathematics of a uniformly advancing shape where you say, well, whatever the tip velocity is, then the velocity should just be related to the local angle by that. But I have another rule, which I just showed you for the velocity. You put the two of those together, and in a coordinate system where you have the radius rescaled by a characteristic length and the z-coordinate rescaled by that same length, shown here, you get a differential equation for the shape, where the derivatives arise just from the trigonometry. And the most important thing about this differential equation is it has no parameters. In this rescaling, there are no parameters of the chemistry or the fluid or anything left. So the shapes that you get are universal. And that's why I call them Platonic, as mentioned in the previous talk, because it's like the square or the sphere. There's no size you associate with the square. It's just a square, however big it is. And the same thing is true here. This is a universal shape. Now, when you look at these things, you think, oh, they're sort of conical. But actually, if you study way up away from the tip, you discover that the shape is the 4/3 power law. So instead of 1, it's 4/3, which means it's slightly bulbous, which is that carrot-like shape that you see when you see stalactites. So we went into Karshner Caverns. So I'll skip that. We went into Karshner Caverns. This is my then student Martin Short and collaborator Jim Bagents. And we took laptops and lighting, and we actually photographed a whole bunch of stalactites and then tried to form an average and see whether they were consistent with this picture. So here are some typical shapes. Here's the noisy, wiggly shape that you get from a real stalactite, radius as a function of z. And then you do a fit, so this is like the goodness of the fit as a function of the one parameter in the problem that you need to scale it, this length scale. You find the minimum. You take a whole bunch of stalactites, you put them together, turn it on its side, and that mathematical form goes right smack through the average. So that's pretty neat, I think, because it says that underneath all of this noisy, wiggly shapes, there is this ideal shape sort of yearning to get out. And so this was kind of interesting, but there are many, many other questions. This is really just the start. For instance, could we understand the ripples that form on stalactites? Could we understand these draperies? All of these things are waiting to be done because we have the basic idea of a growth law, but we have to turn it into this geometrical problem, and that actually is quite a challenge. Now, when we studied this, we thought, so that's the first drawing on the left. We thought, you know, there are actually interesting similarities in shape between stalactites on the left and icicles on the right. Now, I'd be a fool if I stood here and said, well, surely they're the same because, after all, you know, things grow. Well, no, it's much different, right? This is calcium carbonate precipitating because of outgassing of gas. This is icicles growing because water freezes as it emerges from the roof of your house to a colder environment, and heat is diffusing. Now, you could say carbon dioxide diffusing, heat diffusing, maybe it's kind of similar. But we wanted to see if there was a more fundamental connection we could make. Well, actually, it's quite simple. If you, again, look at one of these shapes, what you discover is this, that when water freezes, of course, it gives off heat, the latent heat of fusion. And that heat has to go somewhere, so it goes into the air surrounding the icicle. Now, if there's one thing we know, it's warm air rises. And so around the icicle, this slightly warmer air will move up relative to the much colder air that's far away. Now, this is a standard problem in fluid mechanics if you were to abstract it as just a plate. So I have a plate at a given temperature that's higher than the surroundings. There'll be a boundary layer of warm air that goes up, and you can find the thickness of that layer as a function of the z-coordinate moving up, and it grows like the 1/4 power of position, with parameters that depend on the thermal expansion coefficient of air and the viscosity and other such things. Okay, so if you think about it, the only way that heat can escape is by getting through this layer. And the thicker the layer, the thicker the blanket around the icicle. And therefore, the rate of growth over here will be relatively small compared to the tip, because at the tip, that blanket is going to 0. So the tip grows faster than the rest, which is exactly what happened with the stalactite, because the fluid was pooling there. So you put all of this together, and at this point we had a recipe. The recipe is, here's the thickness of the fluid layer flowing down the icicle, the water. We know that as you go down, the flux of water is decreased by the rate of growth of the ice, so you can calculate the flux of water everywhere on the shape. We know the rate of growth goes like 1 over the thickness of the boundary layer. So you turn a crank, and lo and behold, the shape obeys this differential equation, which again has no parameters, and therefore there's a universal icicle shape lurking around. And the really striking thing, besides the fact that it looks like what you see, at least to these pictures that we found in the web, you see it's very hard to find icicles in Arizona, but very easy in Toronto. And any further questions, you will ask Stephen Morris, who's now become the world's expert on this problem. But the thing is that if you look far up this shape, at the relationship between the z-coordinate and the radius, you get the 4/3 power law again. And that really blew us away. And to be honest, I don't understand exactly how it's emerging all the time. I mean, I can tell you what the math is doing, but the fact that this came out of two completely different problems, I think is kind of interesting, both of which give this Platonic ideal. Okay, so that's two examples of trying to understand patterns in nature. By the way, I should say that, again, you can compare the radius as a function of coordinate, vertical coordinate, and you see, at least with some of the images we first analyzed, that it's quite consistent. Now, apart from watching paint dry, one of the pastimes of the amateur scientist is watching ice melt. In later work, we actually got interested in the reverse problem. So you take a block of ice, and you just stick it in front of a camera, and you watch over several hours as it melts. And what you discover is that although you may have started with a cylinder with all right angles, it very regularly produces this kind of bullet shape on the way toward disappearing. And so this is the reverse process. And I should say that actually we worked very hard to do the imaging for this in a way that would be visually interesting, because it's hard to image ice just in typical ways. But if you use the ideas of dark field microscopy on a large scale and basically have side lights with a black background behind it, you can get this wonderful sharp images that come out. And so this is actually a very interesting problem, which is still a bit unsolved, exactly why it forms that beautiful bullet shape. But when I presented this at a conference a few years ago in Leiden, Oliver Steinbach, who is a chemist in Florida, said to me, well, what if you didn't have melting ice, but suppose you just had a dissolving body, like a lollipop that you just stuck in water. And so this is a glucose cylinder stuck on its side here, but gravity goes that way, which we've redone in the lab following some experiments that Oliver and his student did on this very same problem. And it turns out the same thing happens. You get this beautiful evolution toward a super sharp shape. So again, this is this dark field imaging. So once the sharp tip emerges, you'll see it's very easy to do edge detection from this. And it started basically like a right cylinder, and it formed this beautiful contracting bullet-like shape. And there ought to be a law for that, but there isn't one yet. Okay. All right, so the last thing I want to talk about is hair. And this is a project that we worked on starting some years ago, motivated by and in collaboration with people from Unilever who were interested in the problem of hair tangling and other such issues involving fiber bundles, as we say in physical mathematics. Now, there's a lot of interest in understanding the properties of hair, not only in the personal care industry, but also in computer animation. This wonderful head of hair from this character from the movie Brave is realistic to us because people have figured out how to represent mathematically the properties of large numbers of interacting hairs. But when we first started this problem, we were interested in, as I said, in tangling, but really in trying to understand the physics of the familiar body and volume that you sense with hair, the fact that there's a kind of elasticity to a bundle of hair that you know and love. We all play with our hair and sense that springiness. And so we wanted to try to get into this problem, and we thought that if we could understand something as simple as the shape of a ponytail, that it would be an advance. We also thought it would win the Ig Nobel Prize, and it did. So let's look at a switch of hair. These are standardized switches that we get from a company in Long Island. They have 10,000 hairs roughly. They're about 25 centimeters long. And a typical head of hair has up to 100,000 hairs. Hair grows about 4 nanometers a second, which is about the size of the individual protein molecules that make it up. So it's adding 1 per second. And if we ask about the mass density of hair, which is one of the important things, because gravity does act here, in contrast to some of the comments in the previous talk, we have to deal with gravity. The typical weight is about 6.5 grams per kilometer. Okay, and many of us have several hundred grams of, well, not me, but several hundred grams of hair, so that's many kilometers. Okay, now if you just think about a hair, imagine that this is a hair, and you ask about the energy when it's horizontal or almost horizontal. Well, if you bend it a little bit, it's going to cost elastic energy, and that goes like the square of the curvature times an elastic modulus A. And then there's work that you do against gravity to raise it some height h. So if you just compare these two terms and say there exists a characteristic length, that length will turn out to be the bending modulus divided by the mass per unit length times gravity to the 1/3, and in round numbers that's 5 centimeters. And that's the length below which gravity doesn't matter and above which it does. So if you have a really short haircut, the hair sticks out wherever it wants, independent of gravity, but if it's longer than about 10 centimeters, it starts to bend. In fluid mechanics and elsewhere, we always define dimensionless numbers. So we should define the Rapunzel number as the ratio of the actual length of hair to this characteristic length. So Jane Leakes is probably not here anymore. I think her Rapunzel number is about 5. Mine is not. Okay, so hair has stiffness, hair has weight, and hair has random curvatures. So if you were to take apart one of these ponytails and image them under the microscope, you would see that there are a whole bunch of random built-in curvatures, and it's the work done against those elastic springs that you feel when you compress a bunch of hair. So the question is, how do you build a theory of a bundle of hair? And the answer is, Da Vinci told us what to do. So in the notebooks of Leonardo da Vinci, you will find this wonderful drawing of water going past the supports of a bridge. And he said, observe the motion of the surface of the water, which resembles that of hair, and has two motions, of which one goes on with the flow of the surface and the other forms the lines of the eddies. In other words, there's a mean, and then there are fluctuations around it. And that's how we treat the problem. So if you want to build a theory of a bundle of hair, you basically want to say that there is a measure of how many hairs you've got. Let's call that rho, the number of hairs per unit area in some cross-section, perpendicular to the long axis. And then there's some local angle or vector t that describes the mean orientation of the hairs at some position. And from those two, you can construct an energy that involves the curvature squared, where the curvature is related to that vector t, which is this bending energy, some piece associated with gravitational energy, and then you throw all your ignorance into a term we call U that represents the randomness in the problem. And the key point is actually that that randomness defines a pressure which pushes out and swells the bundle. So I'll just go real fast through this. If you basically say that the problem has a very kind of, we would call it long aspect ratio, so that the number of hairs in a radius r scales like r squared, so that the density is uniform, and where capital R of Z is the edge of the bundle and n is the total number of hairs, you have the simplest picture possible, that at every height, everything is just uniform in density and scaling with the outer boundary. And the other statement to make is that that tangent angle basically just interpolates from 0 in the center to whatever the slope is at the edge linearly. And if you know that, you can actually solve the problem, and you can write the energy in terms of the boundary of the shape. In other words, it's no longer a full three-dimensional problem, it's an effective hair sitting at the edge. And it has its own bending energy and gravity, and its own contribution to the pressure, to the elastic energy. And then from this, you get a differential equation to minimize the energy that involves elasticity, the tension in the filament, which is maximum at the top and 0 at the bottom, the weight, and the pressure. And this is called the ponytail shape equation. And apart from near the clamp, most of the important shape that you see is dominated by a competition between the pressure and this weight contribution. So if I just skip this one, you can actually measure the shape just by taking images of ponytails, and here you have R of Z, and deduce the pressure by just extracting these quantities from the shape. And what you discover is that the pressure, as a function of radius, is a straight line. And that's called Hooke's law. So all this effort, we rediscovered the spring. But that's good, because we can interpret the prefactor in front of this, pi 0, in terms of the stiffness of the filaments and the spectrum of curvatures that they have. And so now we can do a test. This is a test we call experimentum crucis, as Newton had one, which is you take experimental ponytails, real ones, you average over orientational views, and you trim it back. So it goes from this flared shape back to something more conical. And then you do the same thing in the theory. So you go from a Rapunzel number of about 5 to a Rapunzel number of about 1, and you get something that looks pretty close to what you see in the experiment. Okay, so that's kind of the statics of ponytails. But some years ago, the now late, great applied mathematician Joe Keller from Stanford wrote a very beautiful paper and shared the Ig Nobel Prize with us because he was interested in the swing of the ponytail. So, a jogger jogs down the street, her head goes up and down, and yet the ponytail goes side to side. Why is it? And the essence of the simplicity of that question is Joe Keller. And we all aspire to just look at the natural world and go, why is that? And to find some interesting math and science from it. So Joe's famous paper basically said, well, we could think about this several ways. Maybe it's really no more complicated than a rigid rod like a pendulum. Or maybe we have to make a better model and think of the ponytail as an equivalent string. Or maybe it should be an elastic filament, kind of like what I was describing. But the essence of the problem is understood just from the pendulum analogy. So what he did was he said, look, it's like a pendulum whose support is just moved up and down as cosine omega t. And so gravity, which used to just be a constant, is now gravity plus a omega squared cosine omega t. And this is a well-known problem. You take a parameter of the problem, you make it time-dependent, you have a parametric excitation. And thanks to the work of George William Hill and others who studied differential equations with periodic coefficients, we know that when this frequency is related to the intrinsic oscillation frequency of the pendulum as an integer divided by 2, something interesting will happen. And so Joe said, well, we know that the lowest order thing would be k equals 1, and we know how many steps a jogger takes typically per minute. You put the numbers in and you predict, indeed, there will be an instability of the up and down state to lateral motion at exactly that speed. Okay. So we thought it would be fun to actually do an experiment to test this and to explore more generally this emerging field called aerodynamics. Sorry. So I had two wonderful summer students, James Moore and Philip Dufresne, who put together this experiment with me over the summer. So the contraption is a rigid table with a computer and a motor and all sorts of things on the top, holding a ponytail in front of a light box, basically LED array with a diffuser in front, and a high-speed camera trained on this thing and various other lights to help us see what's going on. And this plays jittery, but it's really very smooth in reality, so blame the computer. But this is the up and down motion of a ponytail at about 1.6 hertz, and you see there's a kind of breathing motion. Right? So it's airflow within the ponytail, but it's perfectly stable side to side. Again, that jitter is not real. And then when you go to 2.5 hertz, you get this beautiful instability, exactly as Joe Keller described quantitatively, where you get this perfectly regular side-to-side motion. But the key thing about this is that the frequency of side-to-side motion is 1/2 the frequency of the up and down motion. The signature of this parametric instability is that it's subharmonic. And I kept trying to think, besides the movie, how could I show in an artistic way that it's subharmonic? And then I sort of stumbled upon this picture that I constructed. So this is at the beginning of the cycle. This is halfway through one cycle, completely through one cycle, halfway through the second cycle, completely through the second cycle. And it, I don't know, it looks like modern dance to me, I think. But it really summarizes in just a simple picture a lot of mathematics and a lot of physics in a way that it's hard to describe in words. So I think I'll stop there. Thanks.
Ray? Questions for Ray? Yeah.
I wonder whether you've also explored what might be called the fine structure constant for hair, because the characteristic curliness of hair is dependent on the cross section of the hair. So in a microscope, if you look at a hair, if it's a circular form, then it's going to be straight, and if it's highly elliptical, then it's going to be very, very curly. And so that's my proposed name for the ellipticity in this case.
Well, I will use that henceforth. So I'm familiar with that fact. I've seen electron micrographs, and I know this connection, and I don't really understand how it works, follicle-wise.
Yes.
So I think that this is really quite an interesting question, and we are in a situation now where we can image lots of hairs, high throughput imaging, and I'd like to try to understand the statistics of curly hair and try to relate it back to the growth process, its growth and form, that happens in the follicle. Exactly where does this come from in the growth process? I don't know if anybody knows.
No, I'm personally interested in it because I remember I had a very high ellipticity when I was young, so my hair was like all over the place, even though it was long, and it
Yes.
gradually kind of sunk down over the decades.
Can a sprinter with a very long ponytail excite the second harmonic?
Yeah, just get twice the stepping frequency. So I think yes. Yeah. Right.
In principle.
In principle. Volunteers?
Archie.
Be working. The next problem might be, why is a carrot like a stalactite?
Yeah, I've wondered about that too.
So I also have one further question.
Well, can I just say, it probably has to do with burrowing into the ground, so to speak, or growing into the ground. So that would actually be an interesting problem. Or not just carrots.
I mean, the carrot is like a stalactite because the tip grows faster than the sides. That's all there is to it, really, I guess.
Well, I think we should image carrots. I
I'd
think.
like to say that I have taken in excess of 200,000 images of icicles, and they're all available freely online.
Yes, I should say, Stephen Mars has done absolutely amazing job in controlled experiments on icicles. And they're all online and can be analyzed.
So that's a contribution to art, I guess, is to give
Absolutely.
away all my pictures of icicles. But the interesting thing is that the most important parameter to controlling the shape of an icicle turns out to be the purity of the water,
Yes. Yes.
which is the last one you would have selected, probably. And both stalactites and icicles have these ripple patterns, and they're both basically unexplained. And the key difference between an icicle and a stalactite is obvious when you think about it, but the water is consumed in an icicle. So you can actually have an icicle with water pouring in at the top, which stops,
Yes.
ceases to grow at the tip,
Yeah.
because the water is all consumed before it gets there. So it breaks one of these fundamental scalings.
Yes, for sure. I should say that we see icicles all the time, and they seem to just magically appear, but actually trying to do a controlled experiment in the lab to do it is incredibly complicated.
The stalactite experiment hasn't been done
Yes.
because it's even that much harder.
Yeah, a little longer than a PhD.
Yeah.
Last question. Eve was first, I think. So.
Is there not another regime for stalactites, for very small stalactites, because they grow in hollow tubes
Yeah.
on a small scale? I think it has to do with capillarity, that the way the drop detach from the tip of the stalactite. So is there a
Absolutely.
transition between the two?
Yes, so in fact, it was precisely that drop dripping version of growth that we were first studying in our own case in an electrochemical setup where we saw basically rust tubes which would have a bubble that would linger, precipitate a certain chemical film, then detach but leave a little bit of material at the edge and then accrete a tube that way. And this undergraduate in my lab said, "Oh, that sounds like soda straws." And I said, "What's a soda straw?" And he told me, so the soda straw, you have a hollow tube, water laden with calcium carbonate comes down the center, hangs as a pendant drop. The outgassing happens, you precipitate a film over the entire droplet. It eventually detaches from gravity, leaves a ring of material, and if you do that a few million times, you grow a tube. And so that is a very simple growth law, except that it's very hard to predict how much material you leave behind. But it's completely edge-driven, yeah.
Okay, I think we need to close there for coffee. I just want to slightly change something I said at the beginning. So the Ig Nobel Prize is for work that makes you laugh and then makes you think. Ray's work doesn't make me laugh, it does make me smile. And I think many of us find that with work like this and the incredibly simple work on stalactites and icicles, it's so elegant that you can't help breaking into a smile. It's not funny, but it's just gorgeous. So thank you.
Thank you very much.